Welcome back. So we are back with the second chapter, that is electrostatic potential and capacitance. And capacitance. Okay, so first of all, they are asking us the concept of conservative force. What is a conservative force? Yeah, a conservative force is a force, which it's path independent. That is, look, if I'm taking a ball, why is this allowed? Should make it a ball. Very difficult. Okay, you imagine. Okay, I'm taking a ball, and if I take this ball from this place here, finally to here. So we started it from here, and we reached there. So what is the change in potential energy of this body? You imagine this Earth surface. Yes, it's very simple. What is it? Yeah, final potential minus initial potential. Very simple. So look, first of all, we took this body here, then 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 here. This was the path taken by the body, right? Somewhat similar path was what taken by the body. But hence, if this was the path also, what happened? Yeah, there is no net, but the final potential doesn't depend on the path. It just depends on the initial and final position. The forces which are state variables or which are independent of path is known as conservative forces. So understand, gravitational force, electrostatic force and all are conservative forces. Frictional force is a non-conservative force. It depends on the path. But gravitation, electrostatic, etc. are what? Conservative forces. So that is what told here. Okay. So now we are going to define potential. First of all, what is potential? Potential means what? It is a work done. Potential really means work done. Really, its meaning is work done. It is like potential. If you take potential, gravitational potential, you take example. Gravitational potential means it's a work done to bring a unit mass from infinity to a certain point. It is the gravitational potential. So as that, we are having our electrostatic potential that we'll be learning in the chapter, that is electrostatic potential. It is electrostatic potential, that is defined as a work done by an external force in bringing a unit positive charge from infinity to a point, It is the definition of electrostatic potential. So really, if you need, you can write it as, okay, let us take something. Now let us take, you know that work done is equal to integral f dot dx, right? Integral f dot dx. So if I am taking a point R and I am taking a point P, what I have to do? Yeah, I have to find the work done in taking a thing from here to from here to here. So that what I should do? Yeah, work done from R to P F external dot dx. Right. Dx. Got it? So by this thing, if we integrate, we get the what? Work done. You understand that change in potential energy is equal to UP minus UR. U final minus U initial, that is equal to what? W RP. This is the potential energy difference. So these are normal things told here. What is potential energy? What is kinetic energy, etc., etc., etc. Not that important. Now we come to electrostatic potential. Electrostatic potential. That is first electrostatic potential due to unit charge. That is, I am taking a Q here to find electrostatic potential at this point P. Distance is R. The electrostatic potential is given by V equal to 1 by 4 pi epsilon 0 Q by, here it is 1, so 1 by R, just R. This is the formula for a point charge. What? Potential due to a point charge. Electrostatic potential due to a point charge. Got it? Did you get it? Yes. That's about it. That is important. Now we have a graph here. That is showing us the variation of electric field and potential. Okay. Yes. 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5. Let us take this as what? This as electric or voltage, E or V. This is distance, that is 0.5, 1, 1.5, 2, 2.5, 3, 3.5, etc. So what is happening is that you know that E is directly proportional to 1 by R square, and V, that is potential, is proportional to 1 by R. So what happens? So when we are plotting V, we'll plot it as at 1 it will be equal to 1. Otherwise the graph will be like this. For E it is directly proportional to 1 by R square. Right. So at 1 they will meet each other. These two graphs will meet each other. 1 second. This graph I will draw it some more properly. I can draw the other graph. Okay. Now electric field graph is like this. This is electric field graph and this is potential graph. They can ask you which is electric field and which is potential. Answer accordingly. Very important. Okay. Yes. Understood? Yes. Now we'll do a question. Calculate the potential at point P due to a charge 4 into 10 raised to minus 7 coulomb located 9 centimeter away. Calculate the potential at point P, which is 9 centimeter away. Is a question. It's very simple. Potential. I'll write it as V. P we already used for dipole moment. We'll get consider this. V equal to 9 into 10 raised to 9, 1 by 4 by epsilon 0 into 4 into 10 raised to minus 7 by 9 into SI unit raised to minus 2. So this will be what? 10 raised to 5. So that will be 9, 9 cancel. 4 into 10 raised to 9, 10, 11, 12, 13, 14. This will be the, sorry, 1 second. This is minus 5. Sorry. 10 raised to minus 4. This will be our final answer. This will be volt. This will be our final answer. Now they have asked you something. Look. Potential. I told you that work done is equal to Q times potential. This is another important equation, like force is equal to Q times electric field. This is another equation. Work is equal to Q times potential. Look, really the equation for work is 1 by 4 pi epsilon 0 Q1 Q2 by R. So if you need to find, if I am taking Q1 outside, I can also write it as 1 by 4 pi epsilon 0 Q2 by R. This Q2 by R is what? It is volt potential of Q2 at a point R from it. So it can be written as Q1 into V. Q1 into V, this is Q2, right? V2. This is also correct. Or I can write it like this directly. But in this electrostatic chapter, we have learned that F equal to QE, and hence W will be equal to Q times V. Very important equation. So next, the second part of the same question is that the question that we did. We got 4 into 10 raised to 4 as what? The potential V. They are asking work done for bringing a charge of 2 into 10 raised to minus 9 coulomb. It's very simple. W equal to 2 into 10 raised to minus 9 into 4 into 10 raised to 9. Sorry, 10 raised to not 9, 10 raised to 4. Right? Yeah, 9 minus 4 minus 5. 4 into 8, 10 raised to minus 5 volt. Sorry, it's work done, right? So joule. Important. It's very important to write like this. So understand the starting part. We are going to learn that what? So till now what did we learn? Yes, we learned that work done in doing something is R to P F dot dx, F external dot dx. Another one is that potential work done is equal to what? Yes, Q into V. Important. So these two things only we learn, and the graph important. Now this is only the thing about potential they are telling us, and potential is what? Non-conservative force. That is if I'm having a point A, I'm having a point B. If I'm taking a charge Q from here to the point B like this, I'm taking it from here like this. Also, it is a path independent. Both cases what is same? Yes, both cases potential is same. One second. Sorry. Yes. So W equal to QV we told. Now, so the starting part is only telling this much. It's only telling us these many things. That is potential energy. Now they are also telling some more thing I'm telling about. I'm going to speak about potential energy. It is the energy due to the potential change. Potential energy. Look, potential energy of a charge Q at a point is the work done by the external force in bringing the charge Q from infinity to that point. That's the potential energy. Electric potential is equal to the potential energy. Potential energy. But in case, look, if I'm having a point P, I'm having a point Q. I'm taking a charge Q from here to here, and there is a potential change. Then delta U is equal to the potential energy. Potential energy. Then delta is equal to the potential energy. Don't forget. Okay. So this is the thing that is told in the starting 2 pages of the chapter. Now we learned what is potential, what is potential energy, how is W related to potential, etc., etc. for simple point charge center. Now we are coming to some derivation, especially potential due to an potential due to an electric dipole. It's the next part, dipole, and this is one of the important part of the chapter 2. Important. Consider an electric dipole. Normal. Here derivation for axial and equatorial can be derived from the same thing itself. Same thing itself. Okay. Yes. You know what is an electric dipole. If you don't know what is an electric dipole, please watch my previous class. We have also derived the electric field of that dipole. So now we come to the derivation of electric potential of a dipole. So here we are going to take the dipole like this. Dipole is anything, we will take it like this. This is also a dipole. Yes. 1 second, I will draw it a perfect line. Yeah, this is the dipole. I took it. A dipole. 1 second. Yes. I took a dipole. So I am taking this dipole and I am considering a random point somewhere here. Point P. Distance from Q to P. Distance from minus Q to P. Distance from center O to P. Okay. The inclination of the angle theta. Okay. Perfect. This will be A. This will be A because 2A is the total length of a dipole. And the direction of dipole moment is like this. Now. This is R. This is R. Now we want to find P plus Q, that is potential due to this plus Q charge. V plus Q, right? P means, which will be once again confusion. V plus Q is equal to this plus Q charge. Look, this is not a correct straight line, right? Correct? Is it a correct straight line? No. Look, this R will be given to us. This R will be given to us. This we will consider as R1 and this will be considered R2 because we need the distance from the point charge, then only we can calculate the potential. Now I am going to draw a perpendicular line. I just erase it. Perpendicular line from here to here. Perpendicular line. Now I can find this R1 easily. Right, R1 easily. This is A. This is R. This is R. So if we need to find this R1 is given by this R minus this small part X. Right, minus this small part X. R1 equal to this is X. How to write this X? You know that this angle is theta angle. So to write X, A is hypotenuse of this right angle triangle. So if you write cos theta, we will get it as what? We will get it as X by A. Hence X can be written as A cos theta. So R1 is equal to R minus A cos theta. So therefore V plus Q is equal to 1. Instead of 1 by 4 pi epsilon 0, I am writing it everywhere. It's a long time. First of all, I am just writing it here. 1 by 4 pi epsilon 0. We will just substitute K instead of that. So K into Q by R minus A cos theta. Here no square, don't forget, no square. That is V plus Q. Now V minus Q. We need to get R2. Look, the problem is that R2 is longer than R. R2 is longer than R. So I am just enlarging this R line and I am drawing a perpendicular here also. So this is also theta. Therefore this will be A cos theta. So we have to add R plus A cos theta, we get R2. Therefore R2 is equal to R plus X, that is R plus A cos theta. So K Q by minus Q, right? Minus Q by R plus A cos theta. Now what we will do? We got two of them. Plus Q and minus Q. For getting net, what we should do? We'll add both of them. So V is equal to K, will take common, Q1 by R minus A cos theta plus Q minus Q by R plus A cos theta. Q will take it outside, K Q R plus A cos theta minus R plus A cos theta by R square minus A square cos square theta. Right? Yes. So R is going to be cancelled. R is going to be cancelled. Therefore, V is equal to 2KQ A cos theta by R square minus A square cos square theta. Look, you know that P, dipole moment, is equal to 2QA. 2QA. So P K cos theta by R square minus A square cos square theta is the potential due to dipole. Potential due to a dipole. Very simple. This is simple and only one equation is there. If you substitute theta values, you will get the answer. Now, if you need to get the answer at axial point, that is V equal to KP cos theta by R square minus A square cos square theta. Substitute theta equal to 0 degree. So we get KP by R square minus A square. This will be equal to what? This will be our what? Theta at axial point. Axial point. Now to equatorial point. Very simple. Just substitute theta equal to 90 degree. What happens? We get it as 0. Because numerator becomes 0. Right? Therefore equal to 0. So by this we derive a very important derivation in this chapter. Okay? Yes. Okay. So here I will give you one more equation that I forgot to give in the electrostatic chapter, that is equation for electric field at any point. We have only learned axial and equatorial there. So electric field at any point, there is a formula. Any point there is a formula. Please note it. It is E is equal to KP root 3 cos square theta plus square theta plus 1 by R cube. This is for a short dipole. Only short dipole they usually ask it. Long dipole is difficult. So short dipole, this is the formula. Please learn this and keep. One second, let me verify the formula is correct. I have written somewhere. One second. Yeah, this is the answer. This is very important to learn. If it is a short dipole, A will be neglected. It will be approximately 0. We will be only taking R square. Okay. So by this electric field, potential due to dipole come to an end. Now there is a potential due to a system of charges. It's very simple, just add all the potential. That's the fact. Okay. Now here they are telling you something very important. Note it. Potential due to a spherical shell. They're telling about it. One, look, I'm taking a spherical shell and I'm taking a point outside it, R distance. Sorry, R distance from the center. And this is the radius, that is capital R. Here the potential at the point P is very simple. What is it? 1 by 4 pi epsilon 0 Q by, Q is the charge enclosed, Q Q by R. If it is on the surface, that is, it will be R itself. If it's on the surface, it will be 1 by 4 pi epsilon 0 Q by capital R. If it is inside the sphere, if it is electric field, it would have been 0. But if it is a potential, it is R. If it is 1 by 4 pi epsilon 0, same as on the surface, it's Q by capital R. Very important. This is very important. This is the thing to note here, really. Thing to note here. The inside, it's equal to 1 by 4 pi epsilon 0 Q by capital R. That is the radius of the sphere. Radius of the sphere. Don't forget it. Don't forget. Okay. Yes. Okay. So now by here we come to end of this thing. Now we are going to talk about special surfaces where potentials are equal. That is equipotential surface. Equipotential surface. What is an equipotential surface? I'm just reading or defining equipotential surface. And equipotential surface, potential surface is a surface with a constant value of potential at all points on the surface. It is called as an equipotential surface. That is, look, I am having a charge plus Q. I am taking a point R distance from here, here. Look at this point, the potential is given by V is equal to 1 by 4 pi epsilon 0 Q by R. Look, if I am taking any point here, this Q, R distance from here and all, the equation will be same. The potential will be same. If I draw the locus of, if I am joining and drawing the locus of all these points, what I am getting? I am getting an oval or a circle. I am getting. So that means that this circle, all points lying on this circle are having same potential. That means this circle is an equipotential surface. If I am taking another point, P distance, just P distance from here, and I am drawing a circle where all the P distance point, that is all places are P distance from this is also an equipotential surface. So a charge can have many equipotential surfaces, right? Many equipotential surfaces. So let us look at some of the surfaces. Okay. Another fact is that always equipotential surface, shear surface, is perpendicular to what? Electric field lines. Electric field lines. That is, if electric field lines are going like this from a plus Q charge, and I'm drawing a perpendicular like this, that is equidistant from the center. This line, this is like a screen. I cannot draw it 3D. Very difficult to show that. I'll show you something. I'll draw another way and show you. That is, look, these lines, electric field lines, that's coming from infinite source. If I'm taking a surface like this, look, this surface is really perpendicular to this charge, right? This surface is really perpendicular to this electric field line. But this surface is what? Equipotential. Because it is equidistant. All the points in the surface are equidistant from the source of charge, right? So it's an equipotential surface, and this surface is perpendicular to the electric field lines. So this is what we are trying to prove. Field lines. It's very important. Very, very, very important to understand this. Okay. 1 second. Yes. That's about equipotential surfaces. Yes. Now Example, look, I am taking a positive charge. And I am drawing its equipotential surfaces. It will be what, equal radius from, yeah, this is the equipotential surface. Now if I am taking a positive and negative charge, a dipole, taking a positive and a negative charge, it will be like this. It will be like this. If I am taking two positive charges, then the equipotential surfaces will be like this. Okay, so these are some examples to how to draw equipotential surfaces. They can ask questions to draw equipotential surfaces. Now properties of equipotential surfaces. It's very simple. Whatever we spoke till now are the properties of equipotential surfaces. So now let us write properties of equipotential surfaces. Of equipotential surfaces. What are the properties of this surfaces? That is, no work is done, because there is no change in potential. If there is change in potential, only work is done. If I am moving a point in this equipotential surface, is there any work done? No, because there is no change in potential. If there is no change in potential, there is no work done. So no work done in moving a charge on equipotential surfaces. Look, if I am having two positive charges and this is like an equipotential surface to them, taking a charge, I am taking this charge, and I am moving it along this equipotential surfaces like this. There is any work done? No. Very simple to move the charge. But if I want to move the charge to here, work should be done. To here, work should be done. To here, work should be done. But here, any work is needed? No, because it's an equipotential surface. So no work is done in moving a charge on equipotential an equipotential surface. Now electric field is always perpendicular to the equipotential surfaces. We already told electric field is always perpendicular to the equipotential surface. Another fact is that we are going to write the same statement in another way. What? Equipotential tells us the direction of electric field. Equipotential surface. Look, if I am taking two charges, and what I am going to do is that I am telling that this is an equipotential surface, like this. This is an equipotential surface. And how will I draw the electric field? Or one second. No need that example. This example no needed because it will be confusing. It may lead to confusions. No need. Okay. You just tell equipotential surfaces tells us the direction of electricity. Not electricity, electric field. Direction of electric field. Now, fourth one. Two equipotential surfaces never intersect. That's absurd. We cannot draw a tangent. That's a thing. Two equipotential surfaces never intersect. This is there in every field lines, magnetic field or equipotential or electric field or every lines, they never intersect. That's a very big fact. And next, last point is that equipotential surfaces are equipotential surfaces are closer together in region of strong field. Near the charge, equipotential surfaces are closer because more electric field is there. Away going, like if you are going away from the charge, electric field strength decreases. Equipotential surfaces will be far apart from each other. That's a fact. Equipotential surfaces are closer in region of strong field and far apart in the region of weak field. Equipotential surfaces are closer in the region of strong field and far apart or farther in the region of weak field. So these are the 5 or 6 properties of equipotential surfaces. Learn this, may be asked, can be asked. It is usually asked. That's the thing. Now, potential energy of system of charges. I told you that. Now I'll just write it. Potential energy of a system of charges. Of a system of charges. That is U equal to, this is potential energy for 2 charges, right? This is the equation for potential energy. That's distance 1, 2 means the relative distance between them. For 3 charges, the equation will be U equal to K into Q1, Q2. That is these first 1 and 2 charges and distance between them 1, 2, plus Q2, Q3 and distance between them R2, 3, plus Q3, Q1 and distance between them R3, 1. This is the answer. If you are having multiple, you should write like this and go. And in case of electric field also, electric force also, F equal to K into Q1, Q2 by R12 square for 3 charges. Q2, Q1 by R23 square plus Q3, Q1 by R31 square. This is written. This is what important. It is important to understand this thing. That is, if you want to find the total potential of a system of charges, total electric force or electric field of a system of charges, should add it accordingly. Distance between each charge should be taken and added. That's very important. That is very important. Don't forget. Okay. Now, one second. Okay, this thing is over. Now, potential energy in an external electric field, that we already told. But one thing to understand here is, we told you that potential energy that is equal to work done. That's equal to what? Q into V. So I'm asking you, I'm telling you something is that you know that Q of an electron is what? 1.6 into 10 raised to minus 19 coulomb. And if I'm accelerating this electron through a potential difference, that is delta V of 1 volt, then I can write that potential energy of that electron is equal to 1.6 into 10 raised to minus 19 into 1. That's equal to, potential energy is equal to what? 1.6 into 10 raised to minus 19 joule. Right? You can write it, right? This potential energy of an electron accelerated by what? By unit potential difference. difference is called what? It's called 1 electron volt. That's the reason why 1 electron volt is equal to what? 1.6 into 10 raised to minus 19 joule. This derivation. What is the definition for 1 electron volt? Yes, it is that when an electron of 1.6 into 10 raised to minus 19 coulomb charge is accelerated through a potential difference of 1 volt, then the potential energy stored, or the work, the potential energy stored, or the potential energy of the electron is defined as 1 electron volt. Is defined as what? 1 electron volt. Okay. Yes. Okay. Now we are going to learn a concept or a problem doing method, that is potential energy of a two charges in an electric field. Potential energy of two charges in an electric field. You know, potential energy means change in potential. Potential energy means work done, or Q delta V. That is potential energy. Understand? Potential energy. Energy of two charges in an external electric field. What is the potential energy of a system of two charges Q1 and Q2 located at R1 and R2 respectively? And they are asking us many things. So first of all, what is it? There is an external field somewhere. There is an external field here. I am to bring a charge Q1, Q2 to this field. So first of all, what is the potential energy is equal to total work done. First of all, work done in bringing Q1 to this electric field is what? Q1 into V. That is what potential of this electric field. Then I should bring Q2 to this electric field, that is Q2 into V. Next I have to write the potential between Q1 and Q2, that is what? Q1 Q2 by 4 pi epsilon 0, the distance between them R. This is the total potential energy. So when they ask you total potential energy, calculate everything. Calculate first the work done in bringing one charge to the electric field, the next charge to the electric field, then only you should add. If you write just the difference in what, just the potential between them, 0 marks. You should think. First you have to bring this positive charge to this external electric field, then the charge to the external electric field. Both takes what? Energy. Right, yes. So you should think that and write it accordingly. Okay, yes. Now we are coming to another important part, that is potential energy of a dipole. Potential energy of a dipole in an external field. Now we learned about potential energy of two random charges in an electric field. Right. Now what we are going to learn is that potential of dipole. Potential energy. Don't forget energy. Potential, not potential. Potential energy is change in potential. Potential energy of dipole in an external electric field. So before doing this, we just skipped one part from the electric field and charges when I took it. I purposefully skipped it. I told I will tell it here. So we'll complete everything in a flow. First of all, I am going to take the condition of keeping a dipole in the external electric field. I think this is an external electric field. I took a dipole, that is minus charge, minus Q and a plus Q charge in a dipole. This is 2A. Yes. This is kept in an orientation theta with respect to the electric field. First of all, here the net force is what? Net force is 0, because here it is QE force acting on it, Q into electric field. Here it is minus QE, that is what? Cancel. Net force here is 0. But here there is what? Torque. torque, rotational, torque is here because it's oriented in angle theta. There are two things. There is a force acting on both the sides. A couple is produced. Torque is there. You know this torque is equal to what? Force into perpendicular distance. Perpendicular distance means what? Really perpendicular distance means you think this point is like an what? This point is fixed here. This point is what? Fixed here. This is acting like what? Fixed point. So you have to find the perpendicular distance between plus q and minus q. How to find? This theta is given to us. So this will be 2a sin theta. 2a sin theta. Force is equal to QE. Perpendicular distance is equal to what? 2a sin theta. Therefore, torque is equal to 2QEA sin theta. You know that, one second, you know that 2QA is what? Potential. So PE sin theta. This can also be written in terms of vector as P sin theta is what? P cross E. Both are vector quantities, so it is possible. So this is what is the equation for the torque produced in a dipole kept in an electric field. Okay, very important formula. Derivation is also important. 1 mark അല്ലെങ്കിൽ maximum 2 mark and all they will ask to derive, but mostly they will ask to derive everything together, that is potential energy, torque, etc. Okay, so now we know one fact is that if I am taking external electric field, then I am keeping a dipole plus q minus q here. This is what? 2a sin theta distance. Okay, I am keeping it here. Torque is equal to what? P cross E. In which chapter? In rotation chapter of class 11, I think. You look here also there is a change in potential energy because there is a torque acting on it. Torque is acting on it, right? Torque is acting on it. So therefore what is the work done here? Look, if this is theta 1 and I have to turn it to theta 2 angle, then what is the work that I should do against? Work that I should do here. That's given as tau d theta 0 to theta 1. That is what work is equal to. Tau is theta 0, theta 1, tau is equal to 1, 2, 3 PE sin theta d theta. Okay, d theta. Take P and E outside. Sin theta, when we differentiate, we get minus cos theta naught theta 1. To give away the sign, just reverse the limits. That will be giving us P cos theta into theta 1 theta 0. Theta 0 is initial, theta 1 is final. What angle? So therefore work is equal to PE cos theta 1 minus cos theta 0 minus cos theta 1. This is the answer. This is the work done. So work done to change the orientation of a dipole from theta 1 to theta 2 or theta naught to theta. So what I want to do is that, so we got this much work done. Now we need to find what? Potential energy. The thing is that to get potential energy, I'll just write our given equation, that is W equal to PE cos, one second, PE cos theta naught minus cos theta 1. This is our equation. Now U is, so let us take theta naught as 90 degree, because at 90 degree there is maximum torque. So we are taking that condition. So this will become 0 and this will become what? Cos theta minus cos theta. That is where we are where the next angle is. So therefore potential energy is equal to, that we will represent it by U. Otherwise we will be confused with PE. Many children will cut it and all. So potential energy is equal to minus P E cos theta minus P cos theta. Therefore U theta is equal to what? One second, sorry. That is U theta is equal to minus P dot E, because cos theta, right? So this is the what? This is the potential energy stored in it. Now let us once again verify it. That is, you know that potential energy is equal to QVR1 minus QVR2, final minus initial. Okay, perfect. That's equal to Q square VR1 VR2, that is 4 pi epsilon 0 into 2A. R1 R2 is 2A, total distance 2A, right? This thing, look at this thing. Is it this thing equal to minus P? Sorry, the things we did here till here, no, it's not needed for you, okay? It's gonna NCERT. If you are so interested, you can read through it. Now I'm telling about some special cases. Some cases I'm speaking about. That is one, position of stable equilibrium. When you are keeping a dipole in what? External equilibrium, position of stable equilibrium. At what this is it stable equilibrium? Position of stable equilibrium. Stable equilibrium means potential energy or energy should be minimum. To make energy minimum, we should give theta equal to 0 degree. Then what? U is equal to minus PE cos theta, that is 0, that is equal to minus PE. That is the minimum value. Hence it is in stable equilibrium. Now 2, position of zero energy, that is energyless position. Give theta equal to 90 degree. What you get? You get U equal to 0. So at theta equal to 90 degree, we get what? Position of zero energy. 0. Now from here we can understand once again why did we use cos theta naught as 0? Because we are imagining it from what? Changing from zero energy to to a given constant energy theta 1. Then what's the improving thing is that 0 is gone, so we don't need of 2 thetas, but 0 minus this energy is equal to what? The potential energy of that substance. That way we used what? Theta equal to 90 degree. So U equal to 0, there is what? 0 energy. Now third one is position of unstable equilibrium, that is maximum potential energy. Yes, that is theta equal to 180 degree, U equal to minus PE cos 180 degree. Cos 180 is minus 1 minus 1 is plus, that will be PE maximum. At this case what? Energy is maximum, therefore it is unstable equilibrium. Always a substance want to decrease its energy. So when it is at high form of its energy, it is unstable. When it is low form of energy, only it is stable. You learn in chemistry, physics, everywhere you are learning this. High energy is instability and low energy is stability. That way we call this unstable equilibrium because of high energy, and the other minus P is called stable equilibrium because of its lowest energy. Okay. So by this part is over. That is, this part is over. Now we just skipped one thing in between in this chapter itself. Relation between electric field and electric potential. Relation between electric field and electric potential. Why did we skip it? We'll be explaining it now. Okay, we'll be explaining it now. 1 second. Yes. So we know that work done. 1 second. Yeah. Work done is equal to force into what? Distance. Not electric field. Force into distance. Force external into distance. And you know one more thing is that electric field is equal to what? Force by Q. Force by Q. If Q equal to 1, we can tell that E is equal to F. E is equal to F. So this is equation 1. So we can write, you know that W is equal to dV. That is change in potential. So we can write that dV is equal to F external F by Q. Right. So when Q is equal to 1, E into dr. W is equal to what? 1 second. Minus E. Right. So then we will get that E is equal to what? Minus dV by dr. Differentiate potential, you get what? You get electric field. Differentiate potential, you will get electric field. Minus dV by dr. And what does this negative sign means? That is having a sign Q. As I'm going away from this charge Q. Here the potential is maximum. Right? As what we are going along the direction of electric field, what happened? Potential is decreasing. That's why we give minus dV by dr, because as electric field, if we are going in the direction of electric field, what? Potential decreases. Okay, that's the meaning of that minus sign. And the magnitude of it is given by change in magnitude of potential per displacement normal to the equipotential surface at the point. That's what we wrote. dV by dr or V by R or delta V by delta R. That's the thing. So this was one we kept aside. Now we completed that too. Now, yes, that comes to an end. So by this, the first part of this chapter come to an end. First part of this chapter means about potential energy, work done, dipole, and relation between potential and electric field come to an end. Now we are going to electrostatics of conductors. We told water conductors. They are materials which conduct electricity or allow flow of electricity is called conductors. Now we are going to learn about different types of conductors and their electrostatics. So right, electrostatics of conductors. What is speciality of them? Conductors and insulators were described in the first chapter for sure. We told about water conductors, water insulators, etc. Right? And I hope you know what is conductor because we are learning it from first standard. No, whenever we started learning, from then we know what is speciality of conductors. Now we are going to learn about some properties of conductors. Properties of conductors. 1 second, let me look. Yes. Conductors. What are some important properties? First property is that inside a conductor, electrostatic field zero. Field is zero. It's very important. Yes. Look, in conductors, this is a conductor. You imagine it's a conductor. Okay. What happens that in normal condition also conductor is having free electrons in it. The thing is that always in a conducting substance free electrons come and stand in the surroundings or in the periphery the surroundings. So if I am going inside this and I am considering a point P and I am drawing a Gaussian surface inside here, what is given? Yeah, electric field into dot dr is equal to q by epsilon 0. Is there any q inside the Gaussian surface? No. Therefore what we can write? E dot dr is equal to 0. That means what? Electric field inside a conductor is 0. That is how we tell that inside a conductor electrostatic field is 0. Understood? Yes. Now second property is that just outside the surface of a charged conductor electric field is normal to surface. Electric field is normal to surface. Great. Normal to surface. Great thing, right? It's a very big thing. What is happening? Look, I am taking the same conductor. One second, I'll just copy paste that CC. So it will be looking similar. Otherwise, it will be looking like what a cuboid or something like that. Okay. Look, when I'm taking this conductor, it's a conductor. Okay, perfect. Let me draw this somewhere here. Yes. Look, this conductor is having charges in the periphery. I told you, conductors will have charges in the periphery. Yes. This charges in the periphery will produce electric fields like this. And what is the speciality of this electric field? Yeah, this is what? Perpendicular to the surface. Or you can tell that this surface is an equipotential surface. That's the reason it is what perpendicular, right? So this is what is telling electric field just outside the conductor. Electric field is perpendicular to the surface of the charged conductor. Understood? Yes. Next one is telling us that the interior of the conductor have no excess charge in the static situation. The interior of a conductor have no excess charge in the static situation. That is, in a static situation means like there is nothing is flowing through it. If I am taking a conductor, that means that if there are electrons in the conductor, that means that there are equal protons. Otherwise, if you go and touch a copper wire, a conductor, you should get shocked. No. There are positive electrons, there is negative. There are negative, there is positive. Understand? Okay. There is no excess charge in the static situation. That is in the interior of the conductor. Inside the conductor, there is no excess charge in the static situation. That is, a neutral conductor has equal amount of positive and negative charge in every small volume of the element. And they are telling us that if there is any extra charge in the conductor, it will reside at the surface only. It can't reside inside because it will disturb the equilibrium of the metal. So understand that the interior of a conductor have no excess charge in the static situation. There cannot be any excess charge. Otherwise, we should get shocked when we touch copper and all. It's happening. No. So interior of the conductor should not have any excess charge at the static situation. Now next one is electrostatic potential is constant throughout the volume of the conductor and has the same value on the surface. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on the surface. It is very simple, nothing. I'll just take the first photo and bring it here. Yes, first photo. Look, what's the speciality? The speciality is that I have told you, in case of a sphere, we told that inside the sphere and on the surface of the sphere, the electrostatic potential is equal. This is the same condition. Inside the sphere and on the surface of the sphere, electrostatic potential is equal. Because why? Charges on the periphery of the substance. That's the only reason. That way we are telling that the electrostatic potential is constant throughout the volume of the conductor. Inside and outside it is same. Because inside there is no charge. It's neutral. There is no excess charge inside. Constant throughout the volume of the conductor and has the same value as inside in its surface. That is what? Same, because R is same. Inside also we take it 1/4/0 Q by R in sphere. Outside also we took it as 1/4/0 Q by R in sphere. That is radius, right? This is the same condition. That way electrostatic potential is constant throughout the volume and it is same as inside in the surface. Okay? Yes. Now, yes. The next property and the last property, no, not last. Second last property is that electric field at the surface of a charged conductor is E equal to sigma by epsilon 0 n cap. They're telling that the electric field on the surface of the conductor is sigma by epsilon 0 n cap, where n cap is the direction of the electric field, that is perpendicular. The n cap is perpendicular to the surface of the thing. I told you, if we are having a thing like this, it will be always perpendicular. That's what told by n cap. Sigma is surface charge density, epsilon 0 is what? Permeability. Yes. To prove that, one second. Yes. To prove that, consider a charge conductor of irregular shape. This is a charge conductor, look like amoeba, regular shape. Sigma be the what? Surface charge density, that is Q by what? Area. Okay. To determine electric field at this point, we choose a short cylinder. Let us choose a short cylinder here, cylinder like shape here, and this is electric field perpendicular. This is what? Delta S, that is area, delta S. Choose a short cylinder as the Gaussian surface about this point. The pillbox, this shape is called pillbox, this cylindrical shape. The pillbox means, that the box that we put that drugs and all, right? That sugar pressure and all, drugs and all, that box is pillbox. Gaussian surface about this. The pillbox is partly outside and partly inside the conductor. It has a cross-sectional area of delta S, that is given here. That is delta S. Now this is total area, so it's A itself. We'll do it as S. Total area is S, right? S. Total area is S. Okay. Sorry. Partly inside conductor. It has a cross-sectional area of delta S and negligible height. This is the Gaussian surface. This is the Gaussian surface. Draw it in dotted lines. Inside the conductor, you know that it's already told that electric field is 0. We know. So total flux is from the outer cross. Only outside we are having what? When we are considering total flux, it's only from the surface. So total flux is what? E into delta S. That is this area. This area. Delta S. E into delta S. Now you know that this thing sigma is equal to Q by S. Now what is Q? That is sigma into delta S. That's the area. Delta S. Sigma into delta S. Now by Gauss's theorem, phi E is equal to what? Q by epsilon 0. That is E delta S is equal to what? Q is what? Sigma into Sigma into delta S by epsilon 0. Therefore, electric field we get it as what? Sigma by epsilon 0. N cap. This is the derivation of the electric field on the surface of a charged conductor. Electric field on the surface of a charged conductor, that is sigma by epsilon 0. That is sigma by epsilon 0. Sigma by 2 epsilon 0, you remember? Yes. On a infinite plane sheet, it was sigma by 2 epsilon 0. And sigma by epsilon 0 is also the electric field on a what? Two plates of a capacitor. So remember, all things you should connect and study. You should remember each equation separately also. Don't get confused at all. Don't get confused. Okay. So this is derivation of this thing. I hope you understood. So I am going to explain it once again. Electric field is the surface of which given by sigma by epsilon 0. First of all, take a random what? Conductor, any shape, and I am going to consider what? A area delta S, and at that area I will write Q is what? Sigma into delta S. Q at that area, right? So therefore phi E is equal to what? E into delta S. Now delta S cancels, and hence we get what? E equal to sigma by epsilon 0. Important. And n cap is the direction perpendicular to the plane of the conductor. Yes. Now sixth one is electrostatic shielding. It is like, it's not a special characteristic, but it's a characteristic property. Okay, that is the phenomenon of making a region free from any electric field is called electrostatic shielding. What is it? Is the phenomenon of making a region free from any electric field. Example is that, look, you go outside on a rainy day where there is a thunderstorm. Where there is a thunderstorm, and you are having a car. You are sitting in the car of yours. You are sitting this you imagine as car. It is having what? A metal body covered car. And you are sitting inside the car. What happens that there are lightning. The lightning struck your car also. Nothing happens to you. It is safe. You are safe inside. The reason is that as car is a metal is a conductor. So you are really inside a conductor. You are like you are inside a hollow cylinder or a hollow sphere. You know that inside a hollow cylinder or hollow sphere, field is 0. So that is a property of a conductor, a conducting material that helps you from thunderstorm. So understand that electrostatic shielding is a phenomenon of making a region free from any electric field. Example is this. Another example is you go into a lift, and if you try to call someone from a mobile phone, you cannot get the signal. The reason is that you know that radio waves used in your phone, that is an electromagnetic wave. It has electrical and magnetic field oscillating perpendicular to each other. The problem is that when you go inside a lift, only one of them oscillates. Magnetic field is oscillating, but electric field is not oscillating. Hence, you don't get a connection. The reason is that you're inside a lift. It's fully metal covered. You're inside a metallic body. You are being shielded from any external electric field. That's the reason. Another thing is that keep your mobile phone in microwave oven and try to call into it. What happens? You cannot call, because microwave oven is what? An electrostatically shielded. Inside it is electrostatically shielded. The thing is that from microwave oven outside no rays can come, because that's the reason. If you are using microwave oven and microwave rays are coming out of your oven, it is dangerous to us, right? So microwave oven is a perfect example. Lift is a perfect example for electrostatic field shielding. Okay, yes. Now so these are the 6 properties of conductors. Now we come to another important part known as dielectrics and polarization. This is what we are going to learn now. Dielectrics and polarization. What are dielectrics? Dielectrics are non-conducting substances which will be polarized. Polarized means split into charges. Polarized when kept in external electric field. These materials have no charge carriers, like free electrons and all this, nothing is there. These have no charge carriers. Okay. Example: mica, dry hair, etc. So dielectrics are substances which are non-conducting. They usually don't conduct, but they are polarized. They will be split into positive and negative ions or charges when kept in an external electric field. The speciality of this thing is that these things don't have what? They don't have charge carriers in them, but they have special characteristics that they will get polarized in external electric field. External electric field. Got it? Did you get it? Yes. Now we are going to talk about some types of dielectrics. First one is polar dielectrics. Polar covalent bond. Polar dielectric. What's meaning? The thing is that negative and positive charge are separated in it, like HCl. These are dielectrics. Dielectrics whose molecules are polar. Polar means what? HCl, you consider HCl. Positive, negative. H2O. H2O needed. H2O also. Negative, positive, positive. Remember, that's the thing. Not like this stuff. Sorry. H2O means HOH, positive, negative. Remember? Yes. They are called polar molecules. The speciality of polar molecule is that, look, I am taking a can. I am taking what? A big thing, and I am having polar dielectrices, positive, negative. Polar dielectrices means their positive and negative are what? Positive, negative. It is like this. So when I am taking a molecule, when I am taking this substance, dipole means their dipoles are different oriented. They are in different orientations, right? So when I am taking it normally in my hand, they are differently oriented, and net dipole moment is 0. But the same thing I am taking it and I am placing it in an sorry. Okay, 1 second. The same thing I am taking and I kept in what? External electric field. Where? Electric field. What happens? Yeah. Each and everything will be aligned. Like this. Plus, minus. That is negative to positive. Electric field is like this. It will be aligned with it. Minus plus. Yes, plus minus. So this is now what? Aligned. This is the speciality what happens to a polar dielectric when I am placing it in a external electric field. So this happens. So they are aligned to the electric field, but there is also an opposite force acting on it. What is that opposite force? It is thermal energy. Thermal energy doesn't want this to happen. Thermal energy want to balance it thermodynamically. Thermodynamically means it is like this. Thermodynamically. So this electric field is fighting with thermodynamic stability, and what is having? We are having two opposite factors. When they become equal, it is called what? Equilibrium condition. When they become equal, it becomes equilibrium condition. Understood? Yes. Now I told about polar dielectrics. So for sure there will be what? Non-polar dielectrics. The thing is that non-polar dielectrics, these are molecules which are non-polar molecules. Non-polar molecules form non-polar dielectrics. No need to define it 100 times. We already know by hearing the name. A non-polar molecule is which the centers of positive and negative charge coincide. Positive and negative charge coincide. There is no split in charge. Coincide. There is no split in charge. The thing is that a molecule will be looking like this. There is no split in positive and positive center and negative center will be together. Example what? H2. Positive, negative together. Next one. CCl4. C is positive, Cl4 negative is together. They are non-polar. So non-polar molecules. I am taking these non-polar molecules. So when I am taking these non-polar molecules and I am keeping it, this is in the condition where E is equal to 0. They are simply standing here. If I am taking the same molecules, molecules, and I'm keeping it in. I'll decrease the size of this thing, increase the size of this thing. I'm taking the same thing and I'm making what E not equal to 0. That is, applying an external electric field, what happens is that this what center, that is positive and negative charge, which stood together in the electric field, is disturbed. They want negative one to go the other side, positive one to go the other side. Hence it will become what, dipolized, or it will become what, it will start to have a dipole moment. So it will become like this. It will become like this. It will have a what, induced dipole moment. I'm inducing a dipole moment due to the external electric field. Hence this dielectric is said to be polarized in the external electric field. Hence this is polarized. Just positive and negative together means neutral. When I keep it in external electric field, they positive and negative center split, and hence it got polarized. This is how we explain dielectrics. When we keep a dielectrics, if it is a non-polar dielectrics, it's very visible to us. If it's a polar dielectrics, what happened at starting also they had what, small separation in positive and negative, but when we kept in external electric field, properly they got separated and they got a proper dipole moment. Initially the dipole moment, when we are taking a bundle of it, the dipole moment is 0 because they initially cancelled each other. Even though they had positive and negative separate centers, they cancelled each other. But when they apply an external field only, and proper dipole moment is induced in it. Understood? Yes. Okay. So we completed about polar and non-polar dielectrics. Now we are going to tell about another type, that is linear isotropic dielectrics. Linear isotropic dielectrics. Linear isotropic dielectrics. These are substances for which the induced dipole moment is in direction of field and proportional to the field strength, are called linear isotropic dielectrics. So what is a linear isotropic dielectrics? These are substances for which the induced dipole moment is in the direction of field. So these are substances for which the dipole moment is in the direction of a field, that is electric field, and is proportional to the strength of the field. Proportional to the strength of the field, So what are linear isotropic dielectrics? These are substances which are in the direction of, which have dipole moment in the direction of the electric field and is directly proportional to the strength. Dipole moment increases, then electric field increases, or electric field increases, dipole moment is increased. So linear isotropic dielectrics are substances for which the induced dipole moment is in the direction of field and is proportional to the strength of the field. Okay. Yes. Now we have, okay. Now what is polarization? Polarization means splitting into charges. Many of them will tell this the definition, but according to physically, the dipole moment per unit volume, the dipole moment per unit volume of a dielectric is called polarization. So it is the dielectric moment per unit volume of a dielectric. Dipole moment per unit volume of a dielectric is called what? Polarization. Okay. Okay. Yes. So for a linear, for linear isotropic dielectric, we can write what? We can write P is equal to E. P is equal to epsilon naught phi E into E. Sorry, what is this? What is this chi E? This chi E is called as magnetic electric susceptibility. Electric susceptibility. Electric susceptibility. Electric susceptibility, and this electric susceptibility is like epsilon 0 itself. It is different in different medium. Okay. Now, yes. So electric susceptibility we told. Now we are going to talk out how dielectrics what changes the external field. So that first of all, what is that? Dielectrics in external field. I've taken a polarized dielectrics and I kept it in an external field. Okay, so this is the external field. Minus plus. Minus plus. Minus plus. Minus plus, minus plus, minus plus, minus plus, minus plus, minus plus. So the thing is that when we are considering this side, look, all minus sign came. So this is having a minus sigma charge density. Okay, consider. This side, all positive charges are coming to sigma charge density. You know that from this positive to this negative side, there will be an external, there will be a field that is created. A field due to positive and negative. And if I keep created, right? No, before that, sorry. First of all, I kept a dielectrics. I took a dielectrics and I kept it in external field, and the dipole orientation happened. This is then external field. Now after this dipole orientation happened, look, this side all positive charges, positive side and all came together very closely. So we will take this part as what? Having a sigma charge density. Positive charges came together. Okay, let us take this side to have a positive P, sigma P charge density. All negative charges came here together. So here there is a negative charge density. Look, you are taking a very small area inside, anywhere inside this dielectrics also. There is no net dipole moment because positive, there is no net electric field because positive and negative are very close. But when we are taking at the edge here, very much edge here, there is a concentration of negative, negative charges. And at the end here, there is a concentration of what? Positive charges. So what happened? Here positive charge, here negative charge. There is an external, there is an electric field created inside the dielectrics. That is this thing. Inside dielectrics. So what happened? The net electric field is what now? It is E external minus EP. So what happened? Hence, what happened? Yes, the electric field decreased. The external electric field decreased, right? External electric field decreased. Understood? Yes. That is the fact that you should understand. Now, I'm going to tell you something. Look, if I'm taking two charges, and between that charges I'm going to keep one dielectric slab. You know that there are one positive charge, one negative charge, for sure an electric field is there. And I'm keeping a dielectric slab in between them. The distance between them, I'm keeping them in a dielectric slab. So the force between them changes because electric field is decreasing here. When a dielectric slab is kept, instead of vacuum, I'm keeping a dielectric slab in an electric field. What happened? External, the electric field decreases. Electric field, what happened? Decreases. And here comes our hero. I told you about what? K. Dielectric constant. Dielectric constant. So, you know the dielectric constant, something is there. That is the reason why, look, force initially was force of a medium, force in a medium. So, you go to force air by K. If you are keeping it in another medium, and it's a dielectric, what happened? I told you external electric field decreases. That way we divide the force by E. Force by K to get the force or the electric field. You know, you can write the same as if you are taking unit charge. You can take that is EAR by EK. Right? And here now I am going to tell you something. What is this dielectric constant? Dielectric constant is a specific constant that is different. It's a constant that is what specific for a specific medium, which tells us how much is the electric field decreased when we keep a dielectric in an external electric field. How much is the electric field affected is given by the factor called dielectric constant. Dielectric constant. So dielectric constant is we are having an equation. Dielectric constant equal to K equal to E by, that is external electric field, by E minus EP. This is the same equation. Look. K equal to E air, that is normal electric field by E medium. E medium is what? E air by K equal to K. Yes. So this thing they have written it here. E minus EP. EP is the electric field induced due to the polarization. Okay. So by here we come to an end of the part of what? Dielectrics, that is electrostatic of conductors, and dielectrics come to an end. Now we start another important part in our book, another important part in this chapter, that is capacitor and capacitance. Capacitor and capacitance. Really, what is capacitor? Capacitor is told as a what? It is a system of two conductors separated by an insulator. That is, if a parallel plate capacitor, two conductors, plus, minus, separated by an insulator. Here it is air. Okay. So a capacitor is a system of two conductors separated by insulator. Define capacitor. Capacitor is a system of two conductors. It's two conductors separated by an insulator. Okay. Yes. Okay. So let us consider, they are telling that if there are two conductors, let the conductors have Q1 and Q2 charge. charge, and V1 and V2 voltage. And these conductors can be charged normally as how we charge batteries and all. Just connect it to electricity, it will get the charge, and hence we get the charge. Now what's the principle of capacitor? What is the principle behind it? The principle is that potential difference is directly proportional to charge. That's the principle behind capacitance. Capacitance tells that potential difference across a conductor is proportional to the charge on that conductor. So hence we can tell that V is equal to KQ. This K is given as, K is what? 1 by C. Therefore C is what called capacitance. So C is equal to Q by V. This is the most important result of capacitance. So how we are getting capacitance? Voltage is directly proportional to charge. Voltage is directly proportional to charge. Yes. As you know, this capacitance is what? A constant. 1 by C is a constant. Capacitance is a constant. So capacitance doesn't depend on Q and V. Capacitance really depend on the some physical characteristics of the medium. Capacitance depends on, look, understand, capacitance doesn't depend on this Q and V. Doesn't depend on Q and V. C equal to Q means C is a constant. It's always a constant for a medium. So it doesn't change as Q and V changes. Q and V should change according to capacitance. Capacitance will not change according to Q and V. So capacitance depends on what? Geometrical configuration of the system. That is distance between the two plates, the size of the two plates, area of the two plates, etc. So geometrical configuration of the system of two conductors. That is shape, size, separation, etc. 2. Nature of the dielectric, nature of the insulator. Between these two plates, there is a dielectric medium. So nature of the insulator separating the conductor. Insulator separating the conductor. Okay. So these are the things which are which capacitance depend on is geometrical configuration, and second one is nature of the dielectric or insulator. Okay, got it? Yes. Now what is SI unit of capacitance? SI unit of capacitance, it is farad. Farad, F. That is 1 farad is equal to farad. 1 farad is equal to what? Q by V, coulomb per volume. 1 coulomb per volume. Now symbol for capacitance. Symbol for capacitance. Symbol for capacitance. Yeah. This is the symbol for capacitance. Got it? Capacitance. Capacitor with fixed capacitor. Capacitor with fixed capacitance. Look, there can be variable capacitor also. Capacitors with the fixed capacitance. We only learn fixed capacitance for our convenience and for our level of difficulty. We can also represent one capacitor like this. It has variable capacitance. Just see and keep the figure. Just see and keep. Don't learn it. See and keep it. Yes. Now dielectric strength. Dielectric, one second. Dielectric strength. Dielectric strength. Dielectric strength means it is the maximum electric field. The maximum electric field. Electric field that a medium can withstand without breakdown. It's a maximum electric field that a medium can withstand without breakdown. It's called dielectric. It's called dielectric strength. It's the maximum electric field that a medium can withstand without breakdown is called dielectric strength. Okay, just learn the definition and keep. Okay, this is like, because the dielectric strength really means that air also, if we pass a lot of electric field through air, it will ionize. If ionization happens, it becomes a dielectric. There's a dielectric constant coming, and hence it breaks down and it changes the direction of the electric field, etc. Lot stuff is gonna happen. And what happened? At last there's a big problem. So they're telling you, what is the electric strength of a medium? It is the strength. It is the amount of voltage. It's the amount of voltage, or it's the amount of electric field that a medium can withstand without breakage of its insulating property. Without breaking down of its insulating property. Insulating property means if this electric field go above a specific value, the medium between these two parallel plate capacitors ionizes, and hence they act as a dielectric. Electric field changes, right? So that's the meaning of a dielectric strength. It is the specific strength of each medium for which a maximum electric field can pass through. If it go above that, the medium ionizes. That's the meaning of a dielectric strength. Now we come to the most important part, that is parallel plate capacitor. Parallel plate capacitor. That means a capacitor with two plates. One second. Two plates, one positively charged and one negatively charged. Sigma says minus sigma because negatively charged. Okay. Distance between the plates is D. 2, 1. Area is A. Okay. Yes. So look, now we are going to find out many things from this. First of all, we need to get electric field. First of all, electric field outside both the plates is 0. Because there is no charges. The charges, if they are also, cancel out. So electric field, I'll just name it. This is 1, this is 2. This is 1, this is 2. Electric fields at outer region 1 and 2 E is equal to 0. It's 0. Now electric field between the plates. The plates. Electric field between the plates. That's equal to sigma by 2 epsilon 0 for the above one. For the below one, this minus sigma, right? So minus into minus sigma by 2 epsilon 0. So what happens? It adds up, causing sigma by epsilon 0. This is the same thing. This is the same thing for the electric field at the surface of a conductor. Do you remember? Electric field at the surface of a conductor is sigma by epsilon 0 n cap. So this is same as that. Okay. Now we got E. Now with E we can find it V. You know that V by D is equal to E from electrostatics chapter. Not from this chapter we learned. So therefore V is equal to ED. E we know as what? Sigma by epsilon 0 D. That is V. V is equal to sigma by epsilon 0 into D. What is sigma? Sigma is equal to Q by A. That is area. Therefore V is equal to Q by A epsilon 0 D. A epsilon 0 D. This is the next equation, important. 2. Q by A, Q by D, Q D by A epsilon 0. Now you know that C is equal to Q by V. Capacitance. So C is equal to Q by Q D by A epsilon 0. Q cancel. Therefore capacitance for a parallel plate capacitor is A epsilon 0 by D. Very, very, very important to know. 0 by D. Epsilon 0 by D. Now we are going to another world of dielectrics. We are going back to dielectric world. Effect of dielectric on capacitance. What happens? Very normal. You know that capacitance of a normal parallel plate capacitor is this. Electric field between them is this. What? Q by A epsilon 0. Sorry, one second. Sigma by epsilon 0. That's Q by A epsilon 0. Right. And potential difference is equal to QD by A epsilon 0. Everything you know. Now let us consider another situation. I am taking the same above diagram. Yeah, this diagram. I am just copying it. Yes, a diagram. Now according to this diagram, we derived the above situations. Now what I'm going to do is that I'm just raising these things. Okay, I'm just taking one plate apart so I can once again properly keep a dielectric between it. So now I'm introducing a dielectric slab of thickness what? About some T thickness, and the distance between two plates is still D. Okay, thickness T. Okay. The thing is that from here to here there is what? Electric field coming. And electric field, when it is passing through a dielectric, you know one thing that, yeah, if this is passing through dielectric, minus charge aligned to left and positive charge aligned to right due to what? Polarization, and hence there is an opposite electric field which decreases the electric field. And from here once again positive to negative, the same electric field is going. This is electric field due to polarization, right? So the net electric field, E net is equal to what? It is E minus EP, E naught, or E naught minus EP. Okay. Now therefore V will be becoming V E naught minus V EP. Sorry, one second. V will be becoming E into D, ED. E naught D minus T plus inside this this much part, thickness T, it is E naught minus EP into the thickness is T. Right? Right, okay. So let us write V is equal to E naught D minus E naught T plus E naught P, E naught T minus EP T, E naught T, cancel. Therefore V is equal to E naught D no need, we'll be doing another method. One second. Sorry. Don't need to expand it or it will be going wrong. So we get V is equal to E naught D minus T plus. Now I told you, I have given you before, K is equal to F air by F medium. K is equal to F medium by F air by F medium by, one second, sorry, everything is going wrong, one second. K is equal to E naught by E naught plus P. I wrote it before, I taught it before, right? EP. So hence E naught minus EP can be written as E naught by K. So both the sides we got K. So it's very calm to know it. That is D minus T plus T by K. This is the new voltage. You know what is E naught. Just substitute it. What is it? Q by A epsilon 0. Right? Q by A epsilon 0. That is E. Or sigma by epsilon 0 into D minus T plus T by K. Right? Now what will be capacitance? Q by V. Therefore C is equal to Q by Q into D minus T plus T by K by A epsilon 0. Cut it. Therefore capacitance when a dielectric is between us, what? Dielectric between us A epsilon 0 by D minus T plus T by K. Very important derivation. Okay. If you understand this chapter properly, you can easily derive the same. Okay. I hope you understood the derivation. Now what else? Now there is a special condition inside this itself, that is condition. Look, I told you that I am taking a parallel plate capacitor. Look, instead of keeping a dielectric of thickness T, I am keeping a dielectric of thickness D. That is, full distance between them is colored by a dielectrics. So simply use the above formula itself. What is the above formula? It is to find capacitance. Use the above formula. What is it? Yeah. Yes. A epsilon 0 by D minus T plus T by K. L dielectrics equal to K. Here D and T are equal. So D minus D plus D by K. Therefore capacitance can be written as A epsilon 0 K. From below this will be cancelling. K will be going up by D. So it can be written as what? A epsilon 0 by D is what? Capacitance without dielectrics, right? Without dielectrics into what? Dielectric constant. That will be if D is equal to T only. Otherwise you should use the formula that we derived. Okay. As we introduce a dielectrics, what happened? Capacitance how can we define a dielectric constant? Dielectric constant of a dielectric material may be defined as the ratio of the capacitance of the capacitor completely filled with that material to the capacitance of the same capacitor with the vacuum with it. This by this. So K can be what? We can written as C old by C new. Therefore K is defined as what? It is dielectric constant is the what is the of a dielectric constant of a material is defined as a ratio of capacitance old, this is new, right? This is new and this is old. Sorry. Capacitance with the dielectric constant completely filled within that by the to the capacitance of the material when vacuum is between it. Okay, simple. Now we derived everything for a parallel plate capacitor. Now we come to combination of capacitors, like resistance combination, that is 1 by R1 plus 1 by R2, R1 plus R2, etc., parallel, series combination and all. We are going to learn combination of capacitors. That is one. First on series combination. Derivation for this is important, so we have to do it. Series combination. You know that for series combination, voltage is same or charge is same. For a series combination of resistors, voltage is different and current is the same. For series combination of what? This capacitors, charge is constant and voltage is fleeting or changing. So this is a very long class, I know, 2 hours to 3 hours. Q minus Q. Yes. Plus minus V. Okay. Consider 2 capacitors, etc. is told. You know that let us consider this as C1, C2, C3 capacitors with V1, V2, V3 what? Volume. Oh, not volume, voltages. So you know that total voltage is V1 plus V2 plus V3. That is first equation. Now you know that V1 is equal to what? Q by C is equal to Q by V. So Q by C1. V2 can be written as Q by C2. V3 can be written as Q by C3. Okay. So now what we can do? So now we can write V is equal to what? Q into 1 by C1 plus 1 by C2 plus 1 by C3, etc. Right? Yes, etc. Now I am going to take this Q here, Q to this side. So it becomes V by Q is equal to 1 by C1 plus 1 by C2, etc. Right, just 1 by Q by V is equal to 1 by C1 plus 1 by C2 plus etc. Hence what is Q by V? C. So 1 by C effective is equal to 1 by C1 plus 1 by C2 to infinity. N times. Okay. This is the derivation for series combination of capacitors. So in series combination of capacitors, the effective capacitance is reduced. Is reduced, and effective capacitance will be less the lowest capacitance in the combination. It will be less than the lowest capacitor in the combination. Okay, as resistance itself. So your capacitance is what? When you consider series, capacitance is less. Now parallel combination. Look, from morning I started doing this for you only. Please watch the channel, subscribe. Look, a lot things I taught you, right? Lot things, never ending. My love for your studies, but no one is subscribing, no one is liking. Sad. Parallel combination. The parallel combination of parallel combination of some capacitors. Drawing it. I'm taking 3 capacitors here. You can take n capacitors. Okay, no problem. V. C1, C2, C3. Here charge is different because current is different, right? Q2. V is same. So what we can write? Total charge is equal to Q1 plus Q2 plus Q3 into infinity. You know that? Yeah. You know that Q1 can be written as C1V, Q2 can be written as C2V, etc. Now what I will write? Yeah, I will be writing C1 V1 plus C2 V2, etc. is equal to what? Total Q. Therefore, not C1 V1, C. Now I am taking Q is equal to V. I took it commonly out. C1 plus C2 plus etc, etc, etc. Now I am taking V to the other side. Q by V is equal to C1 plus C2 plus etc, 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 etc. Simply Q by V can be written as what? C effective is equal to C1 plus C2 plus C3. So here in parallel combination, it is what? Adding on. But in resistance, it was in series combination. So when we connect capacitors in parallel, the effective capacitance is more. Effective capacitance increases. Okay, understand? Yes. If you need to increase capacitance, use what? Parallel combination. Now next one is energy stored in a capacitor. In a capacitor. So consider a capacitor and let us take the 2 plates, etc, etc, etc. This also derivation is there. Okay, it's about to be over, no problem. Yes. So once again, consider that I'm taking a capacitor. It is initially what? Uncharged. It is initially the 2 plates be uncharged. So here there is positive charge, here there is negative charge. So what's happening is that some charge from this side is being transferred to this side. This is Q dash is becoming Q dash minus dq. Sorry, minus Q dash minus dq. It's decreasing. Okay, so we have to find the external work to do this process, that is to change it, to transfer charge from one plate to another. Okay, yes. Okay, so let the charges initially in the plate be Q dash and minus Q dash. Then what is the potential difference? It is equal to Q dash by C. Suppose now a small additional charge dq has been transferred from plate 2 to plate 1. So now a small charge dq has transferred from this plate to this plate in uncharged condition. So dw can be written as what? V dq. Right, you know that voltage into charge is equal to work done. You learned it. Work is equal to QV. So dw is equal to V dash dq dash. Now therefore V dash we got it as Q dash by C, right, into dq dash Q dash. Now integrate. dw is equal to Q dash by C integral dq dash. Now take w is equal to 1 by C. Q dash means Q dash dq dash. Q dash by Q dash square by 4 by 2. Therefore work done is equal to what? 1 by 2 Q dash square by C. Okay, this is the work done. Now how can I write Q dash? Q dash can be written as V dash into C, right? V dash into C. Substitute 1 by 2 V dash into C whole square by C. CC. Therefore W is equal to half C V square. It's another way of writing it. Now we can substitute C as Q dash by V dash in this equation. So W is equal to half into Q dash by V dash into V dash square. Therefore W is equal to what? Half into Q dash V dash. This is also equation for work. Q dash into V dash. Sorry, I forgot something. This is 0 charge to Q charge. Totally we have to transfer it, right? So Q charge. So it will become not Q dash, Q. Not V dash, Q. Okay, this is the equation. Okay, completed. Yes. Energy stored in the capacitor. Now, energy density of an electric field. When electric field, we are about to be over. C is equal to what? Epsilon 0 A by D. That we derived it. You know that E is equal to what? Sigma by epsilon naught. Sigma is equal to E into epsilon naught. Okay. So charge on the plate of the capacitor. What is it? Q is equal to sigma A. That's equal to what? E epsilon naught into A. This we wrote it from what? Q by A is equal to sigma. Okay. Energy stored in the capacitor. U is equal to what? Q square by 2C. We derived it. Q square, E square, sigma square, A square by what? 2 into A epsilon 0 by D. Therefore what? Epsilon 0 is cancel. A cancel. So therefore U is equal to what? Half into epsilon 0 E square into A. AD. This is equal to what? This is equal to sorry. This is equal to energy. It's equal to what? Energy in terms of epsilon naught. What is energy density? Energy per unit volume is equal to what? Energy density. So this is energy. To make it energy density, divide this by volume. That is half into epsilon 0 E square A D by volume. Volume is the volume of the space between the plane. That is A into D. AD cancels. Therefore we get it as what? Energy charge density as half epsilon 0 E square. Half epsilon 0 E square. 1 second. Rho E square. So by this everything in NCERT come to an end. Now some last important makeup tips for physics. Let us note from this chapter. One about is common potential. What is common potential? When a number of capacitors are of capacitance C1, C2, C3 etc. and potential V1, V2, V3 having charges Q1, Q2, Q3 etc. are placed in contact, then their common potential is given by. I am taking one capacitor C1, C2, C3 and I am keeping them in contact, then their common potential is given by V is equal to Q1 plus Q2 plus Q3 by C1 plus C2 plus C3 etc. Yes. So what it become? Q1 can be written as C1 V1 plus C2 V2 plus C3 V3 plus etc etc etc, right? C1 plus C2. This is equal to the common potential when they are kept in contact. Just know, sometimes they can ask some out of syllabus questions. You will be trapped if you don't learn these things. Now, if conductors of capacitor C1 and C2 and potential V1 are respectively connected together, a law. Okay. Now, second one. Another thing is that I am taking a conductors of capacitance C1 and C2 and potential of V1 and V2. That is C1 V1, and I am connecting it towards C2 V2 respectively are connected, and a loss of energy take place here. And what is the magnitude of loss of energy? Delta U is equal to half CV square, half C1 C2 by C1 plus C2. They are kept in what? They are in series. They are connected in series. So the capacitance becomes what? C1 C2 by C1 plus C2. Simple. And voltage, we should add them. V1 plus V2 whole square. Only this much. Just we kept in series and we derived the equation. No need to learn. If you have brains, you will derive it. And one more brush up tips. Look. Now I want to tell introduction of dielectric medium into the parallel plate capacitor. Battery is disconnected. So when I am keeping a dielectric when in between a capacitor plate when battery is not connected. When battery is disconnected, then the thing is that I'm drawing a table and I am showing it. Why my slide didn't come from? My God. Yes. Okay. Here before, here after keeping the dielectric slab. Before keeping the dielectric slab, charge was Q. After keeping it, no change in the charge, because charge when battery is taken, charge is constant. Before the electric field was E, now the electric field become E by K. Before the potential was V, now the potential become V by K. Before the capacitance was B, now the capacitance becomes CK. And before the electrostatic energy was U, now it becomes U by K. But if the same thing, and once again drawing this, I'm just copying this and keeping. Yes, I'm just copying. Now introduction, the same thing I'm introducing dielectric medium in a charged capacitor connected to battery. When it is connected to battery. Here before Q was Q, now the Q become Q into K. Electric field become E into E itself, no change. Potential difference also it is V itself, no change. Capacitance becomes C into K, U become U into K. Just learn, just understand. Okay. These two tables, just read through it, that's it. Okay. So by this, the chapter electrostatic potential and capacitance come to an end. Everything needed for your board examinations is covered, and extra things also have been covered. Everything you can also refer this for your entrance examinations if needed. Okay. So thank you. Come back. I will come back with current electricity soon. Thank you.